Welcome everybody. This is Rev Games. We are going to be doing a probability video, mainly around gadgets and what I think a good way to think about running an optimal number of cards would be. Um, my apologies if my throat's sounding a little raspy or my voice is sounding a little raspy. I did catch a cold, so it does make my Jesse Pinkman voice sound a little bit better. Bitch, bitch, Mr. White, bitch, subscribe, bitch, bitch. So that's the upside to it, but um, yeah, my throat feels like shit. So, but what prompted this video was looking through um, some of the statistics with Edison format War League, and one of the highest win rate decks was Machina Gadgets, which caught me by surprise. The issue is that it's a very small sample size, not a lot of people play that, but um, it's one of the like my pet decks, so I kind of just wanted to figure out what the I guess optimal, if you want to call it that, number of gadgets would be to play. For the purposes of this video, we're going to be doing some math, and I just pre-filled in a lot of this. I'll show you how I got it here in a second. Um, but we're going to be doing a 40 card deck. I don't think that's the right number of cards to run, by the way. I think you should be running 3 upstarts and making it like a 37 card deck. Um, just because your win con is solidarity, like you're just not winning if you don't hit solidarity or like a limiter removal or something. You just won't, um, unless you just get very lucky. So like the win rate difference you have between hitting a card like solidarity and not solidarity, or like even hitting a limiter, is so huge that I think you just need to run 37 cards with 3 upstarts more or less. But we're going to be doing it for 40 cards, and I think this is useful not necessarily just for gadgets, but really, if there's any number of cards that are running multiples, maybe that you don't want to see multiple of. So a really popular example of this would be something like Royal Oppression, which you, uh, like especially in Vayu Turbo, like you kind of only want to see one. Like if you draw a Royal Oppression and then you draw a second Royal Oppression, that's just totally dead. Same thing with in stuff like Goat format, Royal Decree. If you're on like Goat, or Goat control, and you're running 3 Royal Decrees and you draw one and it shuts off your opponent's traps, that's great. But then if you just start top decking Royal Decrees, that sucks ass. So really what we're going to be doing here today is kind of a mathematical exercise, and I'm going to try to make this quick just because we're going to jump to a conclusion down here, and I didn't want to bore you with just filling this in, but I'm going to show you how I got these numbers. So here we have the number of gadgets in the deck, so 3, 4, 5, all the way up to 9. I mean, I didn't bother doing like 1 or 2 gadgets just because that like doesn't make any sense. This is going to be opening any number of gadgets, so to jump to this, let's say you're running 3 gadgets, which is what this number is. 40 card deck, 6 card hand size for turn 1. This is the probability of drawing between 1 and 3 gadgets. Um, So as you can see, that's 39.43. So we entered that. I'll just do another one kind of, let's do number 7 actually. This I think will be a good point. So you're running 7 gadgets, and here you would actually enter 6 just because you can't, if your hand size is only 6, you can't open 7. So you could only open 6 gadgets in the worst case scenario. So your probability of opening between 1 and 6 gadgets is 71.14. So I think that should be pretty straightforward on how you kind of like navigate putting this in. And by the way, this is the Yu-Gi-Oh deck probability calculator. It's called Yu-Gi-Oh.party if you just Google it. um, so it's just easier to like do the math with like conditional probabilities like this, because you have to do the probability of like opening one card on your first draw, and then if you draw that card, the conditional probability of drawing another one, and then the conditional probability if you don't draw it. It's just like it's really cumbersome, so this makes it way easier. Onto this, which is opening multiple gadgets. So let's start with 3. This I decided to do between 2 and 3, and some of you are probably screaming at your computer that there's an easier way to do this, which there is, what I'm going to show you guys. But Uh, and then you're running 3 gadgets. This is the probability of opening between 2 and 3. So 5.36, 5.36, and I'll just do it one more time for like, let's just say 5. So if you're running 5 gadgets, probability of opening between 2 and 5 would be 15.42. So I think you get the picture. So if we look at this top row, this is the probability of opening any number of gadgets. So obviously it moves, in uh, directionally like how you'd expect it. So every additional gadget you run, you increase the probability of opening any number of gadgets between 1 and 6. And then on this bottom row, well, I think this is important, is this is kind of what you don't want to happen. The ideal hand for gadgets is opening just one and then some like one for one removal spells and traps and maybe some machina stuff. Um, but you don't want to be opening multiple gadgets. That's usually bad. Um, 2 is okay because you can pitch one with Fortress maybe, but like any more than that, like if you open 3 gadgets, it's that game's basically unwinnable. So this is what you want to happen at the top. This is what you don't want to happen at the bottom. So like for instance, how to interpret this, this would be you have a 21.47% chance if you're running 6 gadgets to open between um, 2 and 6 gadgets in your opening hand. Um, so yeah. Now, what I think the important conclusion we're going to come to here is not either of these numbers, but a function of both of these numbers, which is, and I did like a bunch of variations on this, like taking the roots and because it doesn't necessarily move linearly, and I tried to do like some stuff with like taking it to certain powers, but really the simplest one I think is just taking any minus multiple. Sorry for the coughs and stuff here. But basically what we're going to do is we are going to take the any number minus the multiple number, because that's what we don't want to happen, and we want to find the biggest spread between these two numbers. And voila, this is our output, which is the difference in these two numbers. And this is going to be more or less the probability of opening any hand with just one gadget. And we want that to be as high as possible because that's the optimal scenario. So as you can see, the numbers here. And as you can see, if this were graphed, like if these numbers were all graphed on like a y-axis, it would kind of look like I'll just follow my mouse, like a frown or a concave, if you will. So it would kind of look like this. So this being the top, these being the two bottoms of the frown. So I thought this was pretty cool. Like this does kind of give you an idea of quote unquote what the optimal number of gadgets would be depending on your deck size. And for a 37 card deck, it's actually also this. This number is higher. 43.85 is higher than 43.49. Um, it's by about, what is that, 36 basis points? Yeah. Um, so I mean that's another reason why I think 37 cards is better. You kind of have to pick up those probabilities where you can get them. But yeah, so that's kind of the takeaway. And if you're kind of wondering why, it's because the rate at which you're opening, the marginal difference in which you're increasing the probability of opening multiple gadgets is not linearly related with the probability of you increasing the number of hands that you're opening just any number of gadgets. So like if you were to just look at one or two of these numbers, you'd say, oh, I want to open gadgets like every opening hand, so I'm going to run 9 gadgets. Or like somebody else could say, I don't want to open multiple gadgets ever. I'll just run 3, which of course like neither of these numbers like makes common sense. Um, but where there's like marginal trade-offs on each side, they meet in the middle here, which is really just again the difference of these top two numbers. Um, see, there were a few other things I feel like I wanted to say about this. But if you like this, feel free to like or subscribe. It's always helpful. I feel like there was other shit I wanted to say about this, but now I'm forgetting. Um, yeah, that's about it. I just think six is the optimal number of gadgets, and that's largely what a lot of people have run. I've tried seven in the past, which is it's not too far off. It's pretty darn close. Um, but it does increase the probability of you opening multiple gadgets by right around 6%, about 6.5 almost. So yeah, that's it. Thanks for watching, guys. I'll catch you later. I knew what I was gonna tell you guys, which I forgot to say at the end of that video. So this will take 20 seconds. But what I wanted to say to you guys was there is an easier way to get to these numbers, by the way. You don't have to do like multiple steps. So like if you wanted to get to 43.49, all you would do is have the amount of gadgets you have or whatever card it is. And oh, you just do one and one. Since this is the probability of you just opening one, minimum one, maximum one, so one, of course. So yeah, that's what I was on the tip of my tongue. I just totally forgot what I was gonna say. So like another example would be like with five, you would just switch this number to five. What? Why can't I change this? And then you get 42.29, like here. So yep, that's basically it, guys. This time for real. Thanks for watching. See you later.